So let's move on to explain shortly about R. So what is R? R is a statistical programming language similar to MATLAB and many other tools. It can run. It has the library of R. It contains a large amount of functions and algorithms and machine learning tools. We can uh, implement any type or different kind of models, and we can plot some of the regression or the regression tree, and we can have, I mean, we can do a lot of statistical or mathematical calculation or so it's very powerful tool. And the advantage, the highest advantage of R is that it's free source, and it's free to download, it's free to use. Some other tools are not free, like MATLAB is you need to be licensed for the to use it. So how to install it? We go to basically to RStudio, and then we go to download center, and from there we select. There is also some version that is can cost you, but there is also the free, the open source, or the free version, which basically what you need. So we just need the free one, the free version, and we can just hit the download, and then we find here the options. So select the one is fit on your system. This is to use it for Windows or Mac or Ubuntu or Fedora. So select the one you want and then just simply download it, and it's very easy to download. I have it already installed in my computer, so I don't need to reinstall it again. So here we basically when we have when we so this is the main window, and these are some extra or help tools. I actually just need to import my dataset, and I have options here. I can go CSV or Excel. So let's try Excel here. See, preparing the data to. Sometimes importing Excel doesn't work here with R, so therefore it's better maybe to just install in CSV format. So for that I need to prepare my data. So this is case study 2, and so this is actually the Excel, and this is the CSV. So it's very easy. So you need to open the, if you don't have the CSV, then you need to open the Excel, and you need to save as, and you select CSV, and that's it, save it. So it's already been saved CSV, so I don't need to overwrite it. So it's already saved here. I go again with R. So yeah, see, there's a problem to download using it's installing some packages. Okay, it seems work. I think this is importing Excel. Let's try. So let's try to import Excel. Okay, it's fine, I think. Yeah, it can import Excel. So yeah, either Excel or CSV, both are fine. So we just make sure that the first row has names, and that's it, and then we import. So we have the under this name Kokomo. So we can see summary of the Kokomo. So this is summary. So it show you all the metrics. So the first one is actually the project ID. So don't worry too much about this one. So this is the project name, application, and blah blah blah. And this is the other project, that other data. Remember, we create reliability 2 and data 2, complexity 2 to just because these are in categorical format and these are numerical format. So but what we need now is to create another uh, so we have the estimated effort and we have the actual effort. So what we need to calculate the deviation percentage. So for example, we can call this metric as uh, residual, or we can call it deviation. We can call it deviation, for example. So we can, okay, but before that we need to, okay, so we need to put the name of the data set, and we need to put the dollar sign, and then we put the name of the metric that we want to create, deviation, and here we can also put the Kokomo. So we want the deviations to be the uh, uh, the actual effort minus the, or the, yeah, the actual effort minus the we need to put the name of the data set at every time, and then dollar sign and the metric name, or the metric name. So we need to put the estimated effort. So if we see the now the Kokomo, and we now find a new, so if we go to summary Kokomo, so we can see now a new metric here. So the new metric here show you, so we have, this is the minimum and this is the maximum. So these are all from here to here is the almost the underestimation, and this part here is the overestimated, and here close to the median are the values that have good estimation. So we need to know how the deviation, we can create also another metric, we call it deviation 2. Oops, no, Kokomo. Deviation 2, and this is going to be equal to Kokomo deviation by Kokomo again actual effort. So let's do summary. We see, oh, and this here, so deviation 2, we can see that it gave me now a number. For example, let's see all the number here. So Kokomo deviation 2, so we can see here all the numbers that, so this is 0.32. so when it is 0.32, that means this one is 32% overestimated. When it is minus, that means underestimated. But how, by how much here? This one is 1.99, so this one is like 200% underestimated. So this one is underestimated. Here is, this one is the one of the most accurate estimation, because this one is like 0.0001. So this one is like less than 1%. So this one is very good estimation, and this one also. This one is 0.007. This one close to 1%. Okay, so this one I can code this one as 0 and 1. I can work in this one in Excel and then import it again. I mean, for example, so it's easier maybe to do that calculation in Excel. So I can say deviation here will be equal actual minus estimation. I put these two between sorry, so I put these two number in brackets and then divide them by actual again, and I will get here. So it's more clear here in Excel. So if you see here, and I can do something different, I can go to format cells, I mean just make sure that, and they take percentage, so decimal places I can leave it like 2 or 0, it doesn't matter. So this is show you by percentage here. So these are minus 1.7%, 2%, so these are good estimation, good estimation, good estimation, until here. So this one is no, minus 27%. So this is, I can put this one, I code it -1, and this one 32% overestimated, I code it 1, and so on. So I can go by that manually, or I can create here if statement. I say, for example, if the percentage is between this and that, then make this to be 0. If it is above 20%, then make it 1. If it is less than 20%, then make it -1. Like this one is very huge, big gap between the actual, or big deviation between actual and estimated, or the estimation between the actual effort and the estimated effort. So this one is going to be -1. So you can continue, carry on with this until you finish. So after you finish, okay, to not waste your time, I'm going to pause the video and finish this, and then come back again to continue recording. Okay, so we continue here. So I already created the if statement here. So it's actually, we have 0 good estimation, we have -1 bad estimation, and we have 1 also another bad estimation. So now we need to move this file to, we save it first, and then we move it again to we import it again. So we import, is it no, it's text, so I need import Excel, so because I save it in Excel. So oops, yeah, okay, so we make sure that the new metric are exist, so deviation 0, deviation 2, so these are our metrics. So import. So we have now the Kokomo here, and now what we need to do is we need to do something very important, which is converting from numerical to categorical, because the deviation 2 is -1 or 0 or 1. We want that to be considered as a factorial. So in this case we need to change it. We go Kokomo and deviation 2. This is going to equal, we put this command as factor, so that means is consider this as a factor, and we put the this one again, the deviation 2. So that's mean take this one, or take this one, sorry, this metric, and save it as a factor in this, in here. So it's going to be the same. Deviation 2 is going to be converted from numerical to factorial using this function. So when we go this and we go by we summary, we take the summary of the Kokomo, we find here the deviation is converted. So it used to be deviation 2, it used to be this format, so it is changed now to be -1 we have 77 observation, and 0 we have 8 observation or 8 projects, and 1 we have 8 projects. So after we finish with that, we need now to build the model. So the model we need to use is called repart, or is the regression tree model. So we need to install the package. So we type install package, and then we put the quotation mark, and then inside it we type repart, and then we click. It will take a very short time, shouldn't take very long. Okay, I have a problem with connection here, so I need to try to fix it. Okay, I'll pause this video to fix the issue and then come again to continue. So yeah, it's working now actually, but it takes a little while to finish. It usually takes less than that. Oops, it's failed again. Okay, let me solve it, and then I come again. Okay guys, I'm back, and the issue is fixed. So we don't need actually to install packages because the package is already installed. But what we need is to include the library which contain those packages, or the function. Or so we have the repart. We need to put the command library repart, and then we put another command library repart dot plot. So make sure just to put these two function, and the library will be installed in your R. So then you can build your model. So the model is easily, you give it first name, model 1 you can call it, and then you put this, and then you include the repart function, and here where you need to put the formula is very easy. So you need just to put the formula and comma, and then the data, where the data is from. So my formula is like y equal x1 plus x2 plus x3. So let me write it down here. So this is my formula, y equal x1 plus x2 plus x3 blah 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 blah. So y here is the actual or the outcome, they call it the response variable or the outcome variable. So in my case it's going to be here either the three classes I created, the 1 minus 1, and I changed those to factorial. So this is going to be, which I call it deviation 2. So this is going to be my outcome, and then my metric here is the cost driver metrics. So it's going to be all the metric, reliability, data, complexity, and so on. So it's going to be like 15 metrics. So how to write down that? So you need to first start with the name of the data set, which is Kokomo, and then you put the dollar sign, and then you can go scroll down until you see the metric you would like to choose, or you can write it down. So if I put D, then it's go direct to the metric start with D, then deviate. So DE is bring me to the deviation, so I need to put deviation 2, And then how to, I cannot put equal here. What I put, or the I substitute that by using the tilde sign, which is equivalent to equal. And then again I write the COCOMO dataset. That's mean use the metric inside this dataset. So which metric is going to be first? Reliability, and then plus COCOMO $, and then after reliability, what I have here, I don't need to add reliability 2, just enough reliability, the main metric. So I can put data plus, and I can go for all the other metrics, all the other 15 metrics, and then I put at the end, I put comma, and then I type data equal, which is mean this model should call when I run the model, it should take the data from which dataset? From COCOMO. So I need to put this here, and that's it. So this is going to be my model. So after I finish all the metrics and then I press enter, so I have model 1. So I can type model 1 to just see what's the result, or what's my outcome here. So the outcome here is show you that a small tree, it has one branch only. So this is the root, okay, and this is if some of the metric is not included, that mean they are not they haven't significantly cause any risk. So that's mean the only risk is coming from the reliability. So we have the reliability when it is high or low or nominal, and we have another branch the reliability when it is only very high. So we have this two branch low. So let's visualize that. So how to plot it, we can write down repart dot plot, and then type the name of the model, model 1. So this is our outcome. So we can zoom out that to see my tree. So when it is yes, when reliability is high, low, nominal, then it goes mean. So 89% of the data or of the effort is when the reliability under this classification. So they are actually -1. I mean the underestimation is caused by the so here I have like because I have 3 classes, so at the end I end up, so it seems that exact estimation doesn't have any is not significant here, because I have 89% when it is underestimated only when reliability is equal to these categories, and it's only 11% overestimated, okay, when reliability is very high. Okay, so I can extend with that model. I mean, I can increase the metrics in the model. I go back to model 1 and I add more metric to see how this can change. So after this I add complexity, and I can add another metric. I should include them all to see, and the time. So okay, I increase 2 other metrics, and again I need to see the outcome of this. So when we come here, we see the complexity is even come here, complexity and time is actually more significant to have complexity and time than reliability or data. So we want also to visualize that. So we repart dot plot model 1. So this is okay, this is a different picture now. So we have here complexity when it is high or low or nominal. If it is yes, then so the highest portion actually, which is causing the underestimation, is actually when the complexity here. So if it is yes, then 76% of the projects that are underestimated are having complexity, this categories of complexity, and then the rest of the 24% of the project having overestimation. And who affecting here, or who having, or which one is causing the effect here is the time when it is high or nominal. So when the time constraint is high or nominal, so it's overestimated, 14% overestimated, or either 10% underestimation. So this is actually how to write the model, how to report the results, how to understand, how to plot the result, and how to explain it. Read more about the regression model, and maybe if you go to the some of the tutorials talking about the decision tree, it maybe have some more explanation, maybe better than what I'm doing now, about how to explain the results and what does the result mean. Okay, so what's the numbers, these numbers means. Okay, so usually these numbers are the probabilities, or the, for example, like here is 0.83, so we have like three values, because we have three outcomes. We have three possible outcomes. So we have it's either -1 or 1 or 0. So if we build more metrics, we can see maybe different results. We can see more metrics here included, or more outcome. So try to maybe understand more about the risk analysis topic, and the implementation is not very hard. The main point here is how to interpret the result and how to explain it. So I wish you very good luck. So if you have any questions, feel free to ask, and I will try my best to answer them. Again, this is my email address. You are welcome to send me anytime. Thank you.